Gravity is a force that is experienced by everyone and everything all the time. Every time you jump into the air, gravity pulls you back down. It is the reason why we can ride roller coasters or a snowboard. It is the thing that stops us and everything on Earth from drifting into space, and it is what keeps the moon orbiting around the Earth and the Earth orbiting around the sun. Gravity is a force that acts between two objects. It was first discovered by Sir Isaac Newton in the 1600s when he supposedly observed an apple falling off a tree and landed on his head. This discovery led to the universal law of gravitation. The universal law of gravitation states that an attractive force exists between two masses, m1 and m2, which is equal to the product of the two masses divided by the square of the distance between them and multiplied by the gravitational constant, which is designated with the capital letter G. G has a value of approximately 6.674 by 10 to the negative 11 meters cubed per kilogram per second squared. So the force is large if the masses are large, but decreases as the distance between them increases. Consider the universal law of gravity on Earth. When we're standing on the surface of the Earth, our body is attracted to every other mass on the Earth. But of course, the biggest mass on Earth is the Earth itself. So the strongest gravitational force that we feel is between us and the Earth. The Earth has a diameter of roughly 12,700 kilometers on average, and because its mass is roughly evenly distributed across the entire volume of the Earth, then the average distance between us and the entire mass of the Earth is equal to half of the diameter of the Earth, or its radius, which is 6,371 kilometers. The mass of the Earth is roughly about 6 by 10 to the 24 kilograms. So let's apply this law of attraction between a person on Earth with the Earth itself. Let's call m1 the mass of the Earth and m2 the mass of the person. You see that 3 of the 4 parameters are constant, leaving only the mass of the person as variable. Let's now multiply these 3 constants and create a new constant which we will designate with a lowercase g as its symbol. When we calculate the value of g, we find that it is equal to 9.8, and the dimensional analysis gives us a dimension of meters per second squared. Thus, lowercase g is the acceleration due to gravity on the surface of the Earth that the person with mass m2 experiences. So the force due to gravity on any mass m is equal to the product of the mass and the gravitational acceleration g. This is Newton's second law applied to an object on the Earth's surface. We will talk more about Newton's second law in the forces chapter. In this video, we will look in more detail at the case of motion under the influence of gravity. The first thing to note about gravity is that all objects will experience the same acceleration due to gravity at a constant rate of 9.8 meters per second squared. This is regardless of the size or the mass of the object. This constant acceleration holds true for objects falling on or near the surface of the Earth. The acceleration vector is pointed towards the center of the Earth, so on the surface of the Earth, this will be in a direction that is vertically downwards. Because acceleration causes a change in velocity, gravity will cause a falling object to increase in speed as it falls towards ground. Of course, this is in the absence of any air resistance or any force that opposes the force of gravity. We will explore the concept of forces in a later chapter, so for the time being, we will ignore air resistance. Consider an apple that is dropped from the top of the Leaning Tower of Pisa, which is 56 meters high. If we use the kinematic equations that were described in the previous videos, we can calculate the speed or velocity of the apple as it falls down to the ground. So what is the speed of the apple at 1 second? What is the speed of the apple at 2 seconds? What is the speed of the apple at 3 seconds? We find that the speed at 0 seconds is 0, the speed at 1 second is 9.8 meters per second, the speed at 2 seconds is 19.6 meters per second, and the speed at 3 seconds is 29.4 meters per second. If we plotted the velocity as a function of time, we get a graph that is a straight line. This is expected as equation 1 in our kinematic equations show that the velocity is a linear function of time at constant acceleration. Now let's calculate how far the apple has fallen after 1 second, 2 seconds, and 3 seconds. What is the displacement of the apple after 1 second? What is the displacement of the apple after 2 seconds? What is the displacement of the apple after 3 seconds? If we plot the displacement of the apple from the top of the tower, we find that the displacement follows a curved line. In fact, this curved line is a quadratic. This is expected as equation 3 in our kinematic equations show that the displacement is a quadratic function of time if acceleration is constant. So velocity increases linearly at a constant rate when an object is falling, but its displacement increases much more rapidly with time because of the quadratic dependency of time on displacement. These are some of the characteristics of an object falling under the influence of gravity. The acceleration due to gravity on the surface of the Earth is equal to 9.8 meters per second squared. The direction of the acceleration is always downwards towards the center of the Earth, and the acceleration is constant for all objects regardless of the object's mass.